So if you take a look at that, and, sorry, 3.2. Did I say 3.7?
Yes.
Yeah, I meant 3.2. It's the same as a 7, it's just got a little extra line on the bottom. Yeah?
I know you probably have already said this, but when are we turning in 2.4?
Monday. Okay?
Monday.
All right, so the starter question is the following a true equation? So let's take a look at this right here. I've got secant of x times the sine of x times the tangent of x plus 1. And we're wondering if that actually equals the secant squared. So on 3.1, I gave some kind of general hints. A lot of times it's useful to rewrite everything in terms of two trig functions. What two are those? Sine and cosine. So secant is 1 over cosine, so I'm going to rewrite that. So we'll write 1 over cosine of x. We can write, well, that's already a sine, but we can make it look a little more uniform by putting it over 1, make clear that it's in the numerator. And then tangent is the sine of x over the cosine of x. And then I add 1. So if I were to rewrite this expression right here, I've got a 1 times a sine on the top. I've got a cosine times a 1 times a cosine on the bottom. So that's going to be sine squared x over cosine squared x plus 1. This we should recognize, because if you have a sine over a cosine, that's a tangent. So this would be tangent squared x plus 1. And does that look familiar? I think you're sitting over there. Does that look familiar? Remember those Pythagorean identities I said you ought to have memorized for the test? Now you definitely have this one memorized, because I don't think anybody messed this up on the first exam. Whoops. That's the fundamental trig identity, or the Pythagorean identity. Okay, I can make this a tangent by dividing everything by cosine squared, so that would give me tangent squared x plus 1 equals 1 over cosine squared would be secant squared. So wherever there's a tangent squared plus 1, what is that? That's a secant squared x. So I started off with this ugly mess over here, wrote things in terms of sines and cosines, did some simplification, substituted an identity for this. Okay, sine over cosine is tangent, so that's tangent squared. And then use the Pythagorean identity, and what I find is that ugly mess is exactly the same as secant squared. So is that a true equation? Yes, it is. Okay, and we know this because we can use identities and algebra to simplify this ugly looking side over here so it looks like this side there. It is secant squared of x. Yeah.
Wait, where did the cosine go on the top equation?
This one here?
Yeah.
I divided all three of these terms by cosine squared.
Oh,
Okay, so sine squared over cosine squared is tangent squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. Good? Okay, anything else? Okay, so that's not too bad. What we're going to do today is we're going to learn how to verify identities. We're going to be doing a lot of this. Now this is, I would say, a fairly simple identity to verify. But in order to verify identities, we need to kind of go back and review a lot of the algebra that we know. So let's take a look at this first one right here. It says, find each product. Now, not all of the problems that you have on today's assignment say verify an identity. Some of them tell you exactly what to do, like the instructions do here. It says, find the product. In other words, multiply these together. Now, you could go through and do the problem this way. You could say, well, I'm going to take the 1 and distribute it through. I'm going to take the sine of x and distribute it through. That would be totally fine. If you did that, you'd get a 1. You'd get a minus sine x. When you multiply this one, you get a plus sine x. And when you multiply these together, you get a minus sine squared x. You could do that and then realize those go away. So I've got a 1 minus sine squared of x. Okay, or it would be much better if you recognize this pattern from algebra. If you have 1 plus something, 1 plus a term, and then 1 minus a term, that has a name, doesn't it? Doesn't that sound familiar? It's called a difference of squares, or these are conjugates. Okay? You should be able to recognize that that's going to be a perfect square of 1 minus a perfect square of sine. And then does this look familiar at all? If there's a trig function squared, that's a clue that it might be able to be simplified or rewritten using a Pythagorean identity. So let's take this one right here, sine squared plus cosine squared equals 1. If I move the sine squared to the other side, I'd have this. And wherever there's a 1 minus sine squared, what can I put? I can put cosine squared. So the answer on this problem is cosine squared of x. Now, the instructions on this one said find the product. We found the product, it's this, but what's the simplest way to write this trigonometric expression? Cosine squared is the simplest way. Okay, are there any questions there?
So you have to simplify basically like you would have to simplify a fraction?
Yes, please. Yep. Okay, anything else? Okay, take a look at this one. The instructions here are also to multiply, to find the product of the two of these. But you'll notice that this is a binomial and we're going to square it. If we square a binomial, we get what we call a perfect trinomial square. We get a perfect trinomial square. And if you know that pattern that you worked on in 1010, I'm sure you saw it again in 1050. You use that to complete the square and all sorts of stuff. You should be able to quickly take this and write down, well, this is going to be 4 cosine squared x. What's the middle term going to be? 4 cosine x. And the last term, the constant's going to be a 1. Now, there's not a whole lot that we could do with this. This is the product. There's not really any simplification that we can do. If you had to write out what you'd get when you multiply those together and then collect like terms, that's okay. It's just not as fast or as efficient as using that formula that you learned before. Questions? Okay, so a lot of times we're going to be multiplying things and then simplifying them. Sometimes it's going to be really helpful to factor. So let's take a look at this expression right here. Now the first rule in factoring is what? I hear somebody whispering it. What is it? Take out a common denominator. We call it a common factor, right? Greatest common factor. Well, if you look at the two of these, in fact, if we brought even a 1050 student in here and said, hey, do these have anything in common? They might say something really silly like, yeah, we could factor out the alpha. Could you take out the alpha? No, okay? Doesn't work like that, okay? You'd be pulling that alpha out of a function. Very few functions allow you to do that, okay? And yet we've got to find something in common with this. Well, we know trigonometry. Factor that. Okay, I hear an idea over here and one over here. David, what's your idea? You could maybe rewrite this in terms of sines and cosines and then factor. That would be one technique. Don't write anything down yet. Alexis?
That's what I was saying.
Okay.
Because it's negative, you can take out the square, right?
Kind of take out the square. Yes, this is what I'm after. Take a look right up here. When we multiplied those together, we got a perfect square of the first term minus a perfect square of the second term. Well, isn't this a difference of two terms that are squared? Yeah, so couldn't we factor this using a difference of squares? Okay, that's probably the most efficient way to do this one here. So we're going to do secant alpha minus tangent alpha, and this is going to be secant alpha plus tangent alpha. And that's it. Now, what some people struggle with is they're so used to in a math class getting a number answer or getting some nice, tightly written answer. Okay, this is the answer. All you need to do here is just follow the instructions. Okay, they just want you to factor. Okay, let's take a look at this one here and remind ourselves of a technique that you learned in 1050. What's that? You can factor this. It's kind of an ugly factoring problem, but if you think of it this way, if you said, this is kind of like the variable part, and that's that same variable part squared, you learned a technique called substitution. So we could say u is equal to the cosine of beta, and then we think of doing this problem. 2u squared minus u, minus u minus 1. And then we think of whether or not that factors. Okay. Well, that's a fairly simple trinomial to factor. If you need to use that grouping technique where you multiply the 2 and the -1 together and all that sort of stuff and rewrite it so you can group it, that would be fine. But you're going to have a -1 here and a +1 there. So the only difference between factoring our problem and this one right here is our variable isn't just a plain old u or a plain old x, it's a cosine of beta. But if we do the substitution and factor it this way, our answer on this problem is 2 cosine beta plus 1 and cosine beta minus 1. And if you were to just kind of take a quick glance at this and say, gosh, does this actually produce the right thing? If I multiply the 2 of these together, I get 2 cosine squared beta. If I multiply the 2 numbers at the end, the constants together, I get a -1. These multiply to be positive cosine beta, and these multiply to be -2 cosine beta. So when I add those together, I get negative cosine beta. Any questions there? Okay, so you have some problems on your assignment where they say specifically, we want you to find a product. We want you to factor these problems or something like that. Then you've got a bunch of problems where they say verify the identities. So do something like we did up above. They'll give you an equation and they're basically saying, is this a true equation? Now, the truth of the matter is, nearly every single one they give you is a true equation. It is an identity. Okay? So your job is to verify the identity. Show the algebra and trigonometric work to verify it, to show somebody, you know what, I can take this ugly side right here and I can show you how it turns into this other side. Okay, so let's talk about some general rules. So the first rule is work on the complicated side of the equation. Work on the complicated side of the equation. We've kind of been trained in math to work on simplifying things. And that's what works best. Start with the complicated side and simplify it until it looks like the other side. Okay? Next thing is, use all of your algebra skills. And the algebra skills that we're talking about are skills like factoring, combining fractions, breaking fractions up. That's one a lot of people forget about. Like, for instance, if I had 2x plus 3 over 9, a lot of times we just leave it that way. But in some cases, it might be better to write it as 2x over 9 plus 3 over 9, because then I can at least simplify that part. So breaking fractions up in that type of method. Squaring binomials like we did up above. Multiplying conjugates or difference of squares. Substitution, simplifying complex fractions, whole bunch of stuff. Okay? So all that algebra that you started learning, 5-6 years ago, is really going to come in handy if you have solid skills there. Okay? The next thing, use basic identities that we've already learned in this class. Okay? Sometimes writing everything in terms of sine and cosine can be helpful, but not always. Sometimes if there's a trig function squared, you're going to use a Pythagorean identity, but not always. Okay? So just keep those things in mind. And then this one's really important. People tend to get frustrated when they're verifying identities. Sometimes we'll probably do a problem today where we'll bark up the wrong tree to begin with, we'll figure out what we did wrong, and we'll have to back up and start over. Okay? Not the end of the world. If you're one of those people who likes to do all of your assignments on one single sheet of paper and only on the front side and only on the left-hand side of the paper, you're going to hate this. Okay? Get over it. If you want paper, come and see me. Okay? Dive into the recycle bin. It's going to take a lot of paper to solve some of these, okay? And you're probably not going to do well, I guarantee you're not going to do every one of them right the first time, okay? So be patient and stick at it. All right. There's a list of strategies in the section. You can take a look at that. I've kind of covered or written some of those in a nutshell. There are also exercises that are worked through as examples in the section. You may want to take a look at those. I think we use some of those here in our discussion. So again, some of the instructions, just simplify. So we want to simplify this. Let's see. I've got these are fundamentally just fractions, right? If I'm going to add fractions together, what do I need? I need a common denominator. So I need a sign on this one. I'm going to make them have the same denominator by making them have the same factors in the denominator. On this one, I need a cosine. So I've got a cosine here and here. So my common denominator is sine x, cosine x. In the numerator, I'd have a sine squared x plus a cosine squared x. Well, I've simplified it a little bit. Am I done? Okay, not done, because I recognize this right here as the Pythagorean identity, the fundamental trig identity. So we're going to take this and we're going to say, you know what? In place of the sine squared x plus cosine squared x, I can put a 1. So I've got a 1 over sine of x, cosine of x. Now, that does look a little better than what I started with. Can anybody think of something else we could do with this? Yes, Diana.
Could you separate it and then change them to the opposites of sine and cosine?
The reciprocals of sine and cosine. Very good. So this is a good eye there. So Diana says we should break this up. This is not something we're normally used to doing. We normally like fractions to stay one piece. We're going to take this and we're going to break it into 1 over the sine of x times 1 over the cosine of x. Okay, and at first glance you're thinking, wait a minute, can you do that? Can I have 2 1s on the top? Absolutely. This is a multiplication problem. Multiplying fractions is easy. Multiply straight across on the top, you get a 1. Multiply straight across on the bottom, you get sine x cosine x. This is the same thing, but it's now in a form where I can recognize this. I've got 1 over sine x, and I've got 1 over cosine x. And those, as Diana said, are the reciprocal trig functions. So this is going to be 1 over sine is cosecant x. 1 over cosine is secant x. So that's it. That's simplified. Any questions? Okay, let's slide over and take a look at the next one. Yeah.
Doesn't this also equal from the cotangent plus tangent?
The cotangent plus
If
tangent?
you put
Sure. If we were to write this from the get-go, what is this?
tangent.
Tangent. What is this? Cotangent. So could you write it as the tangent plus the cotangent? Sure. Remember the other day I said there's more than one way to do a lot of these? That's another way to do them. Now, if you check the back of the book, not sure what it has. Okay? Either one of them is pretty simplified. Okay? Neither one of them is an answer in terms of sines and cosines. I mean, if we can write it in terms of sines and cosines in a really simple form, usually that's best. But I'd take either one of those. Okay? Good eye. Anything else? Okay, let's take a look at the next one. This one says simplify here also. So I've got a cosine minus a secant over a secant. Okay, we can split it up. Cosine of alpha. Now I'm going to go ahead and write secant of alpha and then minus secant alpha over secant alpha. Okay, this is a piece of cake right here, right? That is a 1. Okay, but rather than write this as a secant, okay, if I know I'm not going to be able to simplify this, it might be better instead of writing it immediately as a secant, let's just go ahead and write it as 1 over cosine alpha. So that makes this a 1. In order to finish this problem off, I'd flip this over and I'd multiply. So this is going to be times cosine over 1. So this is cosine squared x. Oops, that's a minus, right?
Cosine squared alpha.
Yes, alpha, thank you. Okay, any questions there? Okay, would it be okay to leave it like this? Okay, it wouldn't be the end of the world. If this problem were in the back of the book, it's probably not written like that. Remember, if you've got sine squared of x plus cosine squared of x equals 1, I could get a cosine minus a 1 by moving the 1 over here and moving the sine over there. So that would be cosine squared x minus 1 is the same as negative sine of x, or sine squared of x. So probably a better way to write this would be negative sine squared of x. Whoops. Alpha, thank you. Okay. Any questions? Okay. Factor each expression. Does anybody recognize this?
It's the square.
It is. It's a perfect square. It's a perfect trinomial square. This is a perfect square of 3 cosecant theta. This is a perfect square of 2. If I multiply the two of those together, I get 6 cosecant, and if I double that, I get 12 cosecant. So it fits the pattern for a perfect trinomial square. So I write down the 3 cosecant theta. I write down the 2. I put a quantity squared there, and the only thing I have to figure out is, do I put a plus or a minus? It's a minus on this one, right? Because that you determine that by looking at just the middle term. So there we go. Questions there? Okay, let's take a look at the next one. 1, 2, 3 terms. Always good to remember the first rule in factoring. Take out the greatest common factor. Do I have anything in common? Okay, so I have a cosine of beta. And I'm left with a sine squared beta plus a sine beta minus 2. The last rule in factoring is to always factor completely. Make sure you've broken down everything that could possibly be broken down. I'm left here with, again, a trinomial inside. Let's see. Could I do something like this? Let's just try this out. Since this is a fairly easy one, the way we'd make sine squared beta would be sine of beta and sine of beta at the beginning of both of those binomials. And I need numbers here and here that multiply to be -2 that combine to be +1. Are there numbers that multiply to be -2 and combine to be +1? There are. What would they be? Okay, +2 and -1. The middle one's going to be positive, so we need the bigger one to be positive. Okay, and then I circle this right here. Okay, thank you for saying no. That is not right. You want to make sure that you include all the factors in your final answer, so there it is. Okay, are there any questions? Okay. So now we're to example 5, where we've got a set of instructions. This is the first time that we've been told this. It says, verify that each of the following is an identity. So in other words, that's asking us to show the algebra and the trigonometry to prove that one side does equal the other, that this is indeed a true equation. So again, what was that first general rule? Which side should we work on? Work on the complicated side, because we're really good at simplifying, okay? So I would say the more complicated of the two sides is this side right here. So we're going to work on this side, and we're going to try and make it look like that side. Now, I'm hoping that this isn't too terribly difficult, because on this one, we use the two main rules. And the first one is work on the complicated side, and the second one is usually rewriting things in terms of sines and cosines is really helpful. Okay, because they're the most familiar ones. So if I write this in terms of sines and cosines, this is going to be cosine squared x. I'm going to put that over 1. And tangent is sine squared of x over cosine squared of x. Not much work here at all, because now I just use properties of fractions. I can cancel this factor of cosine squared with this factor of cosine squared. And I've simplified that side, and it is sine squared of x. I'm going to put a box around it, and I'm going to do this just to save myself some work. I'm going to say, look, I started to this side. I did some algebra and some trig. I made it look like this side right there. There, it's true. Okay? Got it? Okay. Ready for the next one? Okay, so let's take a look here. We want to verify that this is an identity, and although cotangent is not my favorite trig function, clearly that side is more complicated. Everything is already in terms of sines and cosines, so that step is done there. So now we've got to rely on something else, either some identities or some algebra that I know how to do. Marcos? Okay, factor out a cosine. We notice that both of the terms on the top have a cosine. So we're going to take out that cosine. So if I take out the cosine of x, I'm left with sine squared of x from the first term, and I've got 3 cosines, so I've got 2 of them left, so that's going to be cosine squared x. That's going to be all over the sine of x. Okay, I can cross this off and call it a 1. It might be good, and we're going to get to a point. I'm going to give you a little project where we do this. It's nice, if nothing else, if you just maybe write yourself a little reminder, or at the very least make a mental note of what you did. This is a Pythagorean identity, the Pythagorean identity, and it equals 1. So down below, because that equals 1, the top is 1 times cosine, so I've got a cosine of x times a sine of x, which is cotangent of x. I've done the algebra and trig to show that this side is exactly the same as the other side. So we just verified that identity. Are there any questions on that side? Sure? Okay, so let's take a look at the other side. These were pretty easy, right? Okay, they get a tad more difficult. Let's take a look at the next one, because remember, you've got to remember a lot of trigonometry, and you've got to remember a lot of algebra in order to get these right. Which side do you want to work on, the left or the right? Okay, they're both ugly. Okay, they're both ugly. This one, I think, is the more complicated one, and I'm going to say this is a general rule also. It's good to make the angle that you're working with the same angle. So at least here they're both an angle of x that we're plugging into the cosecant and the secant. Here I'm plugging in a negative x here, and here an x. I'm not even plugging in the same angle into both of them. Okay? So this is probably the side that I'm going to be working on. All right, now, what identity do I use to simplify that right there? They have names. You're going to need to have them memorized for the test. We went over them on Wednesday. My gosh, we're 48 hours later, so this is kind of a struggle.
That's just a negative. That's just a positive cosine.
It's just a positive cosine of x. It's called the odd-even identities. Okay? Cosine is the only even one, and it's reciprocal. Cosine and secant are both even trig functions. The other four, sine and cosecant, tangent and cotangent, they are odd. So whether you went to the right or the left to get to the angle doesn't make any difference. So this is the same as cosine of x, using an even identity. What did we just say about cosecant?
It's a negative. So
It's an odd, so we essentially pull the negative out front. You could think of it like that, and this becomes positive cosecant x. Okay? And if I were to write myself a little note, I'd just say odd, even identities. Okay? Because one of the things that's a struggle is if you go back and look at this for review, is if you don't make yourself at least some little notes like this, figuring out what you did is kind of complicated. Okay? All right. Ideas here. Okay, don't say anything. I just want you to look at this for a second. Okay, and then another little kind of unwritten rule. Okay, you can't say this is hard and fast all the time, but take a look at this. I have one term over here. This is all one term, one fraction. If I look over here, I have two terms. So that ought to be a clue that maybe we ought to take this side and break it into two pieces. If I've got two pieces over here and one piece over here, let's break it into two pieces so we're at least working with the right number of pieces. So if we do that, I have cosine of x over cosine of x plus cosecant of x over cosine of x. Which looks really good for this one, because that's a 1, and I like that. Plus, gosh, I've got this piece and that piece taken care of. All I need to do is figure out, oh my gosh, that's a cosecant. I've got a cosecant, but I don't have a secant. Now, don't just make it appear by magic, even if you know how it shows up. The way it shows up is this. Let's rewrite this. This is cosecant of x times 1 over cosine of x. This is kind of an unnatural thing for us to do in math. We normally like to put things together and make them simpler, but this is the best way to approach and write this problem right here. Cosecant times 1 over cosine is still cosecant over cosine. But now I can see what to do with this. This is 1 plus cosecant of x. And what is 1 over cosine of x? Secant of x. And now I made that side look like this side over here. So we just verified the identity. Did an odd-even identity. Did some algebra. Did some more algebra. And this last step right here was just, let me write it in black, was just a reciprocal identity. Okay? And even just something like recip reminds you that it's a reciprocal identity, odd-even identity. Just something to remind yourself of what the technique was. Any questions there? Okay, can I slide this over? Okay, because the next one's going to take some space, because that's ugly. Okay, which side's more complicated? Left side's more complicated? Okay. What would you do first on that? If you were going to work on the left side?
Cry.
What's that?
Cry.
Okay, I would cry. I'll give you 5 minutes of crying. Let's say we're time lapse here, so we're done crying. 5 minutes of screaming, too. We'll throw that in there. Can you pull out a 2 cosine of y? And the answer to that is you can't. You can't even pull out a 1 minus. Nope. Because remember, in order to factor this, you've got to have the same factors in both of them. Okay, and I can't cancel the 1 with the 1 because those are terms. I can't cancel a 2 cosine with a 2 cosine because those are parts of terms. I can only cancel factors. Yeah.
Is top a difference of squares?
It's not, because 2 is not a perfect square.
Oh, yeah.
Good try. I think we're barking up the wrong tree here. Let's do this one right here. Any ideas there? Try again. Okay, this is why I want to work on this side. It is possible to do this, verify this identity by working on this side, but it is very, very difficult. Okay, it uses a very seldom used trick. Okay, very seldom used mathematical tool. I'm going to show you a mathematical tool that hopefully you recognize and one that is used all the time. So get used to this. Okay, one thing that we can do, so don't write this down. Okay, if I saw something like this, and I said simplify this, most of you would know that what we do here is we rationalize the denominator. We multiply by its conjugate. We'd multiply by this right here. Okay? You've seen that technique before. Now, we're going to do the equivalent of that here. Okay? When you multiply by the conjugate, I think I even mentioned this the other day, difference of squares is a conjugate. Okay? So, if I wanted to say rationalize the denominator, or the equivalent of rationalizing the denominator, I'm basically going to multiply by the conjugate of the denominator. So let's take a look here. What's the conjugate of sine y minus cosine y? Sine y plus cosine y. Now, I haven't changed this side. I haven't changed it. I've just multiplied it by a funny looking 1. A really funny looking 1. So let's go ahead and multiply these together. Now notice on the bottom, and this is why if you're good at algebra, this is much, much quicker. These have a name, difference of squares, and if you know immediately that that's going to be sine squared y minus cosine squared y, you're in much better shape. Okay, let's take a look at the top. This is a perfect square, sine squared y. The middle term would be 2 sine y cosine y plus cosine squared y. Okay, let's focus on the top for just a second. Does anybody see anything that can be done on the top?
Sine squared y plus cosine squared y equals 1.
Okay, if I were to put the two of these together, that's a 1. Okay, so if I did a Pythagorean identity, this would be, I'm going to write a 1 plus 2 sine y cosine y. And since I've got a trig function squared, I could use a Pythagorean identity on the bottom. Okay, now I'm going to stop right here so you don't have to cry or kick and scream too much. Okay, is this getting us where we want to go? It's actually not. Okay, if you were to do this, this would get us here. Okay, carried that out. Now compare what I've got right here with this. So stinking close. Okay, what's wrong with it? It's upside down, isn't it? Okay, so what we typically do, and this is going to come up in when you take calculus, what we typically do is we worry about, well, let's change the bottom. So we multiply by the conjugate of the bottom. Well, that gave us the reciprocal. We got upside down of what we don't want. We've got a sign difference and stuff like that. So instead of multiplying by the conjugate of the bottom, guess what we're going to do? Multiply by the conjugate of the top. Okay? I know. Okay, I think I mentioned sometimes you're going to bark up the wrong tree. You'll get frustrated. You'll have to use more than one piece of paper. There you go. So we're going to change this, and we're going to multiply by the conjugate of the top. So watch what happens now. I'm still just multiplying by a 1. The top ends up being sine squared y minus cosine squared y. The bottom ends up being sine squared y minus 2 sine y cosine y, and then plus cosine squared y. Now, we did some work. We figured out that we approached it the wrong way, but we were on kind of the right track. We were using the right technique. Look at what we've got now. Focus on the bottom. Sine squared y plus cosine squared y. That's going to be a 1 minus a 2 sine y cosine y. Look at the bottom here and look at the bottom here. They're the same, right? Now if I wanted to, I could reverse the order of this and write this as cosine y, sine y, because it's commutative, right? So I've got the bottom worked out. Let's take a look at the top. On the top, I need to have, well, I need a 1 and I need cosines. I don't need any sines. So I think about that identity, sine squared. I'm going to write it in terms of y. Sine squared y plus cosine squared y equals 1. Well, let's figure out what sine is. Sine squared y would be 1 minus cosine squared y. So I'm going to make a substitution here. Wherever there's a sine squared y, I'm going to put 1 minus cosine squared. So this is 1 minus cosine squared y minus cosine squared y. And I'll slide over here, and look what we've got. 1 minus 2 cosine squared y on the top, and on the bottom, 1 minus 2 cosine y sine y. There we go. Any questions? Okay. Sure? Okay, let's do the next couple then. And I think they get a little easier. Does anybody recognize this?
That's what we did on the other.
Say that again.
That's what we did in example 5.
Okay, if you look at example 5, we took this side and we wrote it exactly this way. And what we did to do that is, so Megan said, well, why don't we just write this as a tangent plus a cotangent? You could do that, and you could even do that here, but we don't want to write it in terms of tangent and cotangent. We want secant and cosecant. So in order to do this problem, you've got to get a common denominator. And notice another hint here. If we're going to take this side and make it look like this side, there are 2 terms here. There's only 1 term here. So we'd have to combine these and make 1 term of it by getting a common denominator. So I'll just quickly show the work for that. Again, we'd multiply this one by sine of theta to get a common denominator, and this one we'd multiply by cosine of theta. So we'd have sine squared theta plus cosine squared theta over sine theta, cosine theta. It's the same work we did on the front side. This is now a 1. Keeping in mind how we did that. Common denominator, then Pythagorean identity. Then we break it into 2 pieces. 1 over sine theta, 1 over cosine theta. Then we've got a cosecant, and we've got a secant. And I've made this side look like that side. I just verified that identity. Okay? But for some reason, when you do this in an identity form, people look at this and go, my gosh, this is way more complicated than what we did on the front. But it's really not. You need to think of it that way. These are just using some algebra and some trig that you've learned. Okay? All right. Good? Okay, so we'll take a quick look at a few of these. It says try a few of these on your own. Ideas on this one? I've got sine and cosecant and cosine and secant. If you write everything in terms of sine and cosine, sine cubed x, 1 over sine of x, cosine cubed x, 1 over cosine of x. Again, I'm working just on this side right here. Cancel that one with one of those. Cancel that one with one of those. So I've got a sine squared x plus cosine squared x equals 1. That's it. Okay, let's take a look at the next one. And the hint here is it's generally easier to simplify expressions. So it would be easier to multiply these together and simplify it than it would be to, what do you see that we can do here? You can factor it. Okay, it's usually easier to simplify than to factor, but if you want to work on this side, both sides work out just fine. So I'm going to go ahead and do this one by multiplying the 2 of these together. What do you notice about this? It's a difference of squares. So you could quickly do this as 1 minus sine to the 4th beta. Now, do we have any identities that have sine to the 4th in them? Let's write this as 1, and then let's write this as sine squared beta, sine squared beta. And what can you put in place of both of those?
For every sine squared, you can put 1 minus cosine.
You can put 1 minus cosine. Okay, so this is going to be 1 minus cosine squared beta. That's also going to be 1 minus cosine squared beta. These are exactly the same, so this is going to be a perfect trinomial square. So this is going to be 1 minus 2 cosine squared beta. And then this is going to be plus cosine to the 4th beta. And look how close we are. Distribute the negative through to each one of those. So this is going to be 1 minus 1 plus 2 cosine squared beta. And that's going to be a minus cosine to the 4th beta. The 1's go away. What? We okay? Everybody all right with that? I just distributed the negative through. So that'd be a negative 1, that'd be a positive 2, and that'd be a negative cosine to the 4th. The 1's are going to go away. So this is going to be a 2 cosine squared beta minus cosine to the 4th beta. And it looks just like that side. So we verified it. Now again, a lot of people like doing this because it's something familiar. We're just multiplying together, collecting like terms, making a substitution. If you want to work on this side and factor out a cosine squared and go from there, that's totally okay. You can make it look like the other side. Yeah?
Where did you get the 2 from the cosine?
Because if you multiply the two of these together, you get 1 when you multiply these together. You get minus cosine squared beta when you multiply these together. When you multiply these two, you get minus cosine squared beta, and then you get plus cosine to the 4th beta. Okay? It's just the pattern for a perfect trinomial square. If you want to multiply the binomials out, that's fine. Questions? Okay. Let's see. Which of these last two do you want to do? You want to do C or D? C? Okay, here's a few more C's. Well, you want to do A again? Okay. All right, let's take a look at this one. They're both kind of complicated. Do you want to do the left side or the right side? Right side. Why?
Because you can just split it.
Okay, you could split it up. That would work. And we could immediately change these into signs. So if you want to split it up, this would be cosecant over cosecant plus 1 over cosecant, which is 1 plus, what is this? Wouldn't that be sine of x? Okay, now, watch please. How on earth do I make this look like that side right there? How do I take a 1 plus sine and make it 1 minus sine squared over 1 minus sine? You could multiply by the conjugate. But if you didn't see that, I can take this and I can multiply it by 1 minus sine of x on the bottom and 1 minus sine of x on the bottom. By the way, does that change this side at all? No, because this is just a 1. It changes the way it looks, but it doesn't change the value or anything. Okay? If you see that, then you can immediately make it look like this side. But if you wanted to stop right here and work on this side over here, and notice that this is a difference of squares. And that I could cancel the two of those. So this side is made to look like 1 plus sine x. This side has been made to look like 1 plus sine x. I could then circle the two of them and say, look, I did some work on this side, I did some work on this side, and I made them look the same. That's an acceptable way to verify the identity. It's not the good way to do it. It's not a preferred way, but it's an acceptable way to do that. Okay? So, practice a bunch. Okay, be patient. Okay, and please take a look at the note at the bottom. It says you can work on both sides to make them look the same, but that's not preferred. Okay, whatever you do, one last thing, whatever you do, don't move a term or anything from one side to the other side of the equation. Why is that not okay? Because what you're assuming there is it is equal to each other. Okay, that those two sides do equal to each other. You're assuming it's an equation. Okay? Okay, between now and Monday, if you take a look at D and E, see if you can figure those out. We'll do some more problems on Monday, and we'll correct 2.4. Have a great weekend.